And we are going to do one more example of a chi-squared hypothesis test. And I'm feeling older and older and older as I continue to teach because none of my students have seen Casino, so no one appreciates this reference. But anyways, go ahead and watch it. We're on YouTube anyways. Ace Rothstein suspects the player is Casino of cheating, so he asks to test if the dice are true. Gives you the following data set for the outcome of rolling 2 dice, 2 six-sided die. Wants to make sure there's no cheating, so he ran the experiment 800 times. Ace Rothstein is a man who appreciates large data sets to work with. Determine if the dice are true at a 99% confidence interval. So, similar as before, null hypothesis, frequency is same. Alternative, they're different. Hopefully they're not. That player's sick, or else there's dire consequences. What is my confidence interval? 99%. Or my alpha is equal to 0.1. Or I have to calculate my chi-squared experimental. And then 5, my chi-squared alpha nu. So, nu is equal to k minus 1 minus r. Are we asked about basically distributions? No, that's in the next video. So again, this is 0. What are my number of outcomes? So if I flip basically the sum of 2 six-sided die, I can get 2, I can get 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So my number of possible outcomes should be 11 that we're dealing with. So k minus 1. So nu is equal to 10. So chi-squared experimental 0.01, 10. If I look back at my chi-squared table, I will find 0.01, 10 again. Should have remembered that. Is equal to 23.209. So if I look now at my distributions, so this is the distribution of my sum of my die. So again, I'm going to count how many from 2 to 12. The probability should just be, again, not equal this time, but again, you can kind of convince yourself of this 1/36. The most probable obviously should be that in the middle here. So you can kind of convince yourselves of that. We'll do a problem with basically poker and cards and pulling cards. So if you multiply that by the length, that probability times the length of your list, that will give you, basically this is the probability 1/36 to get 1, 1/36 obviously to get 12, and then this would be, or actually this is 2. So this would be 2, 3, 4, 5, 6, 7. Yep. So these are your probabilities. These are the expected values once you multiply by the total number of rolls, that length rand. And now you can calculate your chi-experimental values. So this is a gigantic value. Why is that? Because we generated basically a random number list. So they should not follow that distribution, as we might expect. So we go back, look at our distribution, and let's look at our test. So this is my chi-squared alpha, so that's 23.209. So this is reject, this is do not. And we will get here, right here, so our way over on this side, this is our chi-squared alpha nu is equal to this. Way over here, this is our chi-squared experimental, and that is equal to 297.26. Again, because we randomly generate those numbers. So we fall in the reject region. So the dice are not true. So that player is in deep, 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 deep trouble. And you know the penalty if you watch Casino. So you can kind of appreciate that. So again, these are kind of just, again, they're probabilities. So whether it's basically flipping coins, random number generator, if there's, again, some probability due to, again, the number of different configurations for dice and how to, obtain, a value of 2 or 3 or 4 or 5 or 6. That's what we're looking for with these chi-square tests when we're looking at, are our materials true? Are the frequencies the same? And so in the next video, we're going to use, we're going to actually test a little bit something a little bit more complicated, which is, are my rolling velocities normally distributed? So we're going to look at a set of data, see what we're given, what are our observed values versus our expected values, and see does our sample at a certain confidence level appear to be normally distributed, or is it basically governed by some other distribution function? So that's about it. We'll get into that next time, and I will see you all in the next video. Thanks. Have a good one. Bye.